Tonight's lodging is a hotel with infinitely many rooms. Room 1, Room 2, Room 3, an endless corridor. But tonight it's completely full. In the dead of night, a single guest opens the door. There are infinitely many rooms, but everyone is taken. Is it a no vacancy turn away? The manager calmly switches on the microphone. Everyone, he asks, please move just one room over, to the room numbered 1 higher. The guest in room N moves to room N+1. And just like that, room 1 is empty. A full hotel just confirmed a room for the new guest. And here a weighty question arises. Even an infinity that can take infinitely many more guests, does it have a size? Astonishingly, the answer is yes. And not all infinities are even the same size. Some infinities are overwhelmingly larger than others. And today, the only weapon we need to measure them is Cantor's one-to-one correspondence. First match. Which is bigger, the natural numbers or the even numbers? The evens look like just half of the naturals. Since the evens sit entirely inside the naturals seem to be more. But in the realm of infinity, intuition doesn't always hold. Here's the rule. If two sets can be paired off one-to-one with nothing left over, we consider them the same size. We pair each natural number n with the even number 2n, 1 with 2, 2 with 4, 3 with 6. Take any even number 2k, and its partner k is always there. So the natural numbers and the even numbers are the same size. The whole and what looks like half of it are equal. Welcome to the world of infinity. Now we raise the stakes. The integers, which carry along 0 and the negatives too. Stretching both ways, they look about twice as many. The trick is to zigzag. Start at 0, then alternate 1 negative 1 positive, sweeping through every integer. Written as a formula, we send the odd natural numbers to n-1/2 and the even natural numbers to -n/2. That way, every integer gets called out with none left behind. Here are the two matches so far redrawn as arrows. No arrow overlaps or goes missing. The integers, even dragging along 0 and the negatives, are the same size as the naturals. Another draw. This time the opponent is the rational numbers. Fractions, that is, every number expressible as an integer over an integer. Look only between 0 and 1, and they're already infinitely dense. But then someone has a brilliant idea. Take a fraction p/q in lowest terms, put the numerator p on the horizontal coordinate, and the denominator q on the vertical coordinate, and plot it as the lattice point pq. Now the once dense rationals turn into points dotted across the plane. And if they're points, then maybe, just maybe, they can be counted. Two cautions. Reducible points are left blank, and 0 counts as a reduced fraction only when its denominator is 1. So every spot, 0q, with denominator other than 1 is blank as well. Now the heart of it. Start near the origin and spiral outward, assigning a sequence number to each lattice point as you meet it. 0 is first, 1 is second, -1 is third, 2 is fourth. Skipping over the reducible blanks as we go. Let's catch our breath with a midpoint recap. Natural numbers, integers, rationals. Each looked bigger than the last, yet all three end in a draw. So a suspicion creeps in. Could it be that all infinities are, in the end, the same size after all? The final boss that shatters that suspicion arrives in the next chapter. Now the real numbers versus the naturals. The reals, which fill the number line without a single gap. Will this one be a draw too? The conclusion first. The reals are an infinity overwhelmingly larger than the naturals. The run of draws ends right here. Cantor's weapon is the diagonal argument. The strategy is proof by contradiction. Assume it works, then dismantle that very assumption yourself. If the reals could be counted, then the reals between 0 and 1 would have to be lined up in a list with none left out, each spelled out as a decimal. The key is the diagonal. Take only the first digit of the first number, the second digit of the second, the nth digit of the nth, and collect them. Now we twist this diagonal one digit at a time. If a digit is 1, change it to 2. If it isn't 1, change it to 1, building a new number d. Since d is made only of 1s and 2s, it also dodges the trap of numbers with two representations. The picture shows the final blow. The red is the diagonal, and the yellow number beneath it is d. Compare them, and the new number differs from the first number in the first digit, from the second in the second digit, it's off by at least one digit from every single row of the list. So D is nowhere in the list. Since for any list you bring you can build a number it missed, the reals cannot be counted. This was the moment Cantor, with a single line of diagonal, first proved that infinity has tiers. Time to give names to what we've seen. An infinity you can count off in order 1, 2, 3 like the natural numbers is called a countable infinity. It doesn't mean you finish counting, it means you can pin a number tag 1, 2, 3 on every element with none left out. We gave this countable infinity's size a name. The Hebrew letter aleph with a 0 attached, aleph-null. The smallest infinity in all the world of infinity, the very first step. The naturals, the integers, and the rationals all pass the same number tag game, so they're all aleph-null. On the scale they weigh exactly the same. But the reals were different. This larger infinity, which the net of countability can't catch, is called an uncountable infinity. The size of the reals sits at the far end of this chain, 2 to the aleph-null. It means all the reals have the same size as the interval between 0 and 1, as the infinite binary sequences, and as the power set of the naturals. Let's look only between 0 and 1. Every real in this interval can be written as an infinite binary sequence. Zeros or ones running on forever after the decimal point. Start with the easy intuition. Each place holds only one of two things, a 0 or a 1. For n places, the count is the number of repeated permutations 2 to the n. And since that number of places, n, stretches infinitely across all the natural numbers, it naturally leads to 2 to the aleph-null. Mind you, raising to an infinite power like that is a bit of cheating, so the real proof is left to set theory. Now let's do it properly. We pair each infinite binary sequence with a subset of the naturals. The rule is one line. If the nth digit is 1, put the natural number n into the subset. The power set of a set of size A has size 2 to the A. Since the naturals are aleph-null, their power set is 2 to the aleph-null, and the reals are exactly that too. One last question. We measured the interval between 0 and 1, so why is it equal to all the reals? The answer is the tangent. It grabs a finite interval by both ends and stretches it out to infinity, unfolding it into the entire real line. As x goes to 0, it dives to minus infinity, at 1/2 it passes exactly through 0, and as x goes to 1 it shoots up to plus infinity. Every single point of the interval lands on a point of the line, a bijection. So one interval, small enough to fit in your palm, has the very same cardinality as all the reals. And here lay an aftershock even Cantor never saw. The man who pushed it to the very end was Alan Turing. The story begins with this question. How many computer programs are there in all the world? A program, however long, is in the end a finite string. And finite strings like the rationals can be counted off in a single line. Line them up shortest first, ties broken alphabetically, and every program gets a finite number. Plainly aleph-null. To compute a real number means there's an algorithm that, on input n, pins down a rational with an error 2 minus n. 1/3 the square root of 2 pi and Euler's number e are all in this club. But the membership cards, the programs, total only aleph-null of them. The guests, the reals, number 2 to the aleph-null. There are overwhelmingly too few seats. Even if you subtract the computable numbers from the reals, the size doesn't shrink. That is, the uncomputable numbers are still 2 to the aleph-null. Almost every real number is uncomputable. And it's not just the count. The computable numbers have measure 0, so if you throw a dart at the number line, with probability 1 it lands on an uncomputable number. What's even more chilling is that even describing them in words is mostly impossible, because even the describable numbers number only aleph-null. Drawn in a single image it looks like this. The bright dots are numbers we can name or compute, dust of measure 0. The sea of light filling the spaces between them is the uncomputable reals. Paradoxically, you can even point to a specific uncomputable number. The prime example is Chaitin's halting probability, omega. Omega is the probability that a random program halts. It's a well-defined real number, converging between 0 and 1 over a prefix-free code. And yet no algorithm outputs its digits. The definition is crisp, but computing it is forever impossible. At the root of all of this lies a single thing: Cantor's diagonal. A generation later it was inherited by Gödel's incompleteness, and then again by Turing's halting problem. The proof of the halting problem is the very same move as the diagonal. Assume an all-powerful decider, then feed it to itself, twisting the diagonal into a devil's program that breeds a contradiction. Look, the very same shape as the diagonal table from Chapter 4 appears again. Cantor flips a digit, Turing flips whether it halts, only the target changes, the weapon is identical. To sum up, Cantor's diagonal does its work twice. In 1891, the reals are uncountable. In 1936, the halting problem is unsolvable. And in between lies the truth that almost every number is silent. The long, long odyssey of infinity draws to a close. The conclusion is as shocking as it is simple and beautiful. Even infinity comes in different tiers. The naturals, integers, and rationals are a countable infinity you can tag with numbers. Aleph-null. The reals, by contrast, were an uncountable infinity that one line of diagonal kept beyond counting, 2 to the aleph-null. One step further, asking whether 2 to the aleph-null equals the very next infinity aleph-1, is the famous continuum hypothesis. The answer, astonishingly, is that there is no answer. The continuum hypothesis turned out to be an independent statement in the ZFC axioms, provable neither true nor false. This story didn't stay confined to pure mathematics. The taxonomy of infinity was, in fact, the core logic of what the computer of this universe can never know. Starting from the +1 trick of a full infinite hotel, we've walked all the way to the secret that infinity has tiers, and the silence draped over the very edge of computation. Summed up in 4 lines, it's this. Infinity is compared by one-to-one correspondence. The diagonal argument proves the reals are uncountable. The continuum hypothesis asking after their size has no fixed answer. And the same diagonal drew the very limits of computation. Infinity, it turns out, isn't all the same infinity. If you enjoyed today's video, please subscribe and like. See you in the next Odyssey.